Good morning. Today is Wednesday, March the 18th, and today we're going to talk a little bit about rotational speed. If you think back to when we were first starting this course and we talked about things moving with a certain speed, we were always referring to it moving in a perfectly straight line. But now that we're talking about circular motion and things that are spinning around, we have to talk about what we call rotational speed. Now, rotational speed is very different than linear speed, because linear speed, remember, from September and October is simply the distance that you move in a given unit of time. So, miles per hour, meters per second, that sort of thing is what we're talking about here. And so, when you're driving in a straight line up the Northway, right, you're traveling with a linear speed. Now, if you're going around a curve, you still have speed, and it's not just rotational speed. If you're traveling around a curved path, like for example, if you look at the arrow and the cursor moving around here, these green vectors represent what we call tangential speed. They're kind of the go-between between linear speed and rotational speed. And so the tangential speed is the actual speed of something that's traveling in a curved or circular path, right? Measured again in miles per hour or that sort of thing. And the tangential speed of an object that's located halfway over this disk is going to be less, is going to be less than the tangential speed of something that is traveling out here at the edge of the diameter. On the other hand, the rotational speed is how fast something is spinning as we move, the number of rotations per unit time. And everything on a rotating platform has exactly the same rotating speed, or rotational speed. All right. For example, if you look at the turntable here on the desk, I got to hold my laptop here, so it's a little screwy, but notice that both of these masses spin around the same circle in the same period of time, and therefore they have the same rotational speed, even though the one that's closer to the center has a smaller tangential speed. Okay, the tangential speed in and of itself is proportional to the product of the radial distance, in other words the radius, and the tangential speed. So that brings us to example number, I think it's example number 1, which part of the Earth's surface has the greatest rotational speed about the Earth's axis. All right, there it is, example number 1. All right, so if this represents the Earth, okay?
It's 10 o'clock.
Thank you, Jesus. And if it is rotating around and around and around, all right, which spot on the globe has the greatest rotational axis? Is it up here toward the North Pole, or is it down here at the equator? Well, because the equator has the greatest radius or diameter here, as it spins, this part of the ball is actually moving faster than a part up here as it spins around. Okay? I'm sorry, I read that wrong. It's the rotational speed is equal for both. All right, this point and this point rotate at the same rotational speed. However, in terms of tangential speed or linear speed, the second part of the question, the answer is different. Right, the part down here is moving faster than the part up here, because this part is spinning in a smaller diameter than this part down here. All right, it's spinning in at a much greater distance from the center of the Earth. All right, so if we look at the two questions again, which part of the Earth's surface has the greatest rotational speed about the Earth's axis? The answer is neither. They both have the same, or all of them have the same rotational speed, because they spin once every 24 hours. All right, no matter where you are on Earth, a day is 24 hours long. The second part of the question says, which part has the greatest linear speed relative to the Earth's axis? And the answer there is the some spot that's on the equator of the Earth, because it's traveling in a circle with the greatest circumference. If you're closer to the North Pole, you're spinning with a circle that has a much smaller circumference. Okay? All right. This brings us to then example number 2. All right? Example number 2 reads, on a particular merry-go-round, the horses along the outer rail are located 3 times farther from the axis of rotation than the horses along the inner rail. If a boy sitting on a horse near the inner rail has a rotational speed of 4 revolutions per minute, that's what RPM stands for, revolutions per minute, and a tangential speed of 2 meters per second, what will be the rotational speed and tangential speed of his sister, who is sitting on a horse along the outer rail? Okay, before we answer this question, let's think about what we know about rotational speed and tangential speed. We know that the tangential speed depends on how far we are from the center or the axis of rotation. But the rotational speed is the same for all objects rotating around that same axis. So we know that if the boy has a rotational speed of 4 RPMs, the little girl has a rotational speed of 4 RPMs as well. If the little boy has a tangential speed of 2 meters per second, and the little girl is 3 times farther away, then we can calculate what her tangential speed is this way. All right, so have a look. So in this case, I'm going to make a laundry list of all of the terms that we have here. All right, we know I'm going to call number 1 the little boy and number 2 the little girl. So the value for the rotational speed 1 right here is 4 revolutions per minute. The value of the tangential speed 1 for the little boy is 2 meters per second. I know that the formula for rotational speed is tangential speed divided by the radius. Okay? And so the radius 1, or radius 1, whatever it is going to be the tangential speed divided by the rotational speed. In the case of the little boy, the radius is going to be 2 meters per second divided by 4 revolutions per minute, which gives me 0.5 meters as his radius. Now, the radial position of the little girl, R2, is going to be 3 times the radial position of the little boy. And so 3 times 0.5 is 1.5 meters. All right, think about that. The R1 is 0.5, R2 is 3 times 0.5, or 1.5 meters. Now, that means that the rotational speed for the little girl is still 4 revolutions per minute. We know that because the rotational speeds are the same. Since the rotational speed of the little girl is equal to her tangential speed divided by the radius, her tangential speed is going to equal her rotational speed times her radius. That's going to equal 4 revolutions per minute times 1.5 meters. 4 times 1.5 is going to give her a tangential velocity of 6 meters per second. Okay? All right. So that's essentially the answer to that one. Okay? So the rotational speed of the sister is also 4 revolutions per minute. Her tangential speed is 6 meters per second. Since the merry-go-round is rigid, all the horses have the same rotational speed. But the horse at the outer rail is 3 times the distance from the center, and thus has 3 times the tangential speed. Think about that. The tangential speed of the little girl is 6. The tangential speed of the little boy was only 2. All right, 2 times 3 gives you 6 revolutions, I'm sorry, 6 meters per second. All right. Question number 3, example number 3, says trains ride on a pair of rails. For straight line motion, both rails are the same length. All right, that makes sense, right? 2 parallel lines traveling in a straight path must be of equal length. But which side is longer for a curve? The one on the outside or the one on the inside of the curve? Right? Well, if you think about this and you've got a pair of rails that are going around a curve, you know that the outside track has to be longer because it is essentially a circle with a greater radius, a bigger radius, and therefore it's going to have a greater circumference. Okay? So the outer rail is going to have a greater circumference and therefore a greater distance than the one on the inside. If you have any questions about either of those things, please feel free to get into touch with me. Send me an email at grap@lasalleinstitute.org. Now, your homework for this evening is to do the worksheet 9-2. I will attach it to the topics section for today's work. You should be able to download it and print it out. If you can't print it out, just write your answers on a separate sheet of paper, and I will collect it when we come back to school on whatever day we come back. I will talk to you soon. Stay healthy, be well, and may the force be with you.